I'm going to talk today about computing with generic trees in Agda. So, independently typed programming, one of the useful abilities that you have is to write code that works generically across a range of data types rather than being specific to a single data type. So the example of this that I'm going to talk about today is W types, which let you be generic across a range of recursive data types. Oh, thank you. So the simple example that we're going to start with is these binary trees. This is a recursive data type. A binary tree is either a leaf or a branch consisting of two binary trees. And so from the W types point of view, we would look at this and say, this is a recursive data type and it has two shapes. The shapes are either leaves or branches. The leaf shape has no subtrees and the branch shape has two subtrees. So then we can write the completely generic definition of what a W type is, which is something of a mouthful, but it says a W type consists of a set S of shapes, and then for each shape S, there's a set of places, which are the positions where there might be a subtree appearing, and then a node of the tree is given by a particular shape, so in our case that would be leaf or branch. Then for each place of that shape, a subtree, and then that describes a node of the tree. So in this view of the world, we can write the same binary tree types by saying that the shapes of a binary tree are either leaf or branch. And then the definition of binary trees is it's a W type where the shapes are leaf or branch, and the places are leaf has no places, the type of its places is the bottom empty type, and branch has two places, the type of its places is bool. So then from that definition, we can say the leaf constructor is make a leaf, and when you have to fill in its subtrees, then you say, well, there are no subtrees. And the branch constructor is make a branch, and when you need to fill in its subtrees, the one for false is the left, and the one for true is the right, because false and true are the two constructors of the Boolean type. So this is a very well-known way of encoding recursive data types in a generic fashion. This is a very standard thing to do in dependent type theory. The trouble is, at least in intentional type theory like Agda, it doesn't actually work. And the reason it doesn't work is because we've encoded what looks like it should have been two things, the two subtrees. We've encoded all of these tuples as though they are functions. We've gone straight to a higher order encoding of everything. So that means if we want to talk about things being equal or compute on them, then we have to think about equality of functions, and that gets very messy very quickly. So to show what I mean, we're going to try writing the induction principle for binary trees. So the induction principle says, if I'm trying to prove something about all binary trees, so here's the property I'm trying to prove, and I know that it's true for leaves, and I know that if it's true for the left and right branch of a branch node, then it's true for the branch node itself, then that should be enough to prove it for all trees. So let's try implementing that induction principle, which is the one that we would expect to have for this recursive data type. So we have a tree, we case split on the different cases of this tree, and we get, there's leaf and branch. And now we've got leaf, and x here is the subtrees, the function from places. So x is a function from bottoms. That's x describes all 0 of the subtrees of a leaf. So we should say, right, that one is true by p leaf. And of course, Agda complains at this point, and we can't make any progress. And Agda's complaining because we have a proof p leaf that works for the empty collection of subtrees. And the thing that we have that we're trying to operate on is this other empty collection of subtrees x. And two functions from the empty type, although, I mean, mathematically there's only one function from 0 to anything else, those are not definitionally equal in Agda, and those are not equal in any system where you don't have like a lot of functional extensionality. We've exactly the same problem in the branch case, because if we try to use the branch constructor, we'll also get an error because we have this type x, which is a function from bool to subtrees, and we only have a branch constructor that works for functions which are of the form false is this one, true is that one, and we don't know that an arbitrary function of Boole is actually of that shape. So this is quite annoying, and at first glance it kind of seems like this might just be a limitation of Agda, that why can't Agda see that any two functions from 0 to a are in fact the same. But there is, like, not only does this trick not work, it fundamentally can't work. There's a nice example, I think due to Conor McBride, of what would happen if you tried to make this work by allowing all of these functions to be equal. Actually, I'm just going to delete this code that doesn't work. So if we extended Agda to claim that all functions bottom arrow a were in fact equal, then if we were in an inconsistent context, so there was something of type bottom in scope, then this expression that says lambda x true applied to the inconsistent thing would be equal to that expression, lambda x false applied to the inconsistent thing, because both of those are equal functions being applied to equal arguments. So that would tell us that true would be equal to false in an inconsistent context. So that would tell us that to determine whether true was equal to false, we would first have to decide whether our context was inconsistent. And so we can't, in general, decide whether something of type bottom is provable from a context. So if we were to try and make these equal, to make that trick work, to make the induction principle actually compute, then we would immediately break decidability of definitional equality and the type system would stop working. So there is a workaround for this, which I'm going to go through next, and that is if we didn't encode the places in W types as functions, but we just said there's going to be a list of places, then the equality for lists is much more well behaved. Those are a first order thing. We don't have to think about whether two functions are equal. But it does limit us to talking about just finitary trees, where each node has only finitely many subtrees. So to do those, I'm going to present that by first encoding finite types in Agda. So here's, rather than going straight to lists, we're going to describe what a finite type is. So often finite types are described via Nash, that the finite types are the numbers from 0 to n, and then there's only one finite type with 5 elements in it. But I'd really like to not do that. I'd like to make these not be unique, because it's quite useful to talk about, like, it's not particularly useful to equate, to say that every type with 2 elements is Boole. It's useful to give things names. So I'm going to say that the finite types contain none, the empty type, 1, which is a singleton type, and I'm going to give it a string for a name, and plus the disjoint union of 2 finite types. So then once we've got these types, we can interpret them into sets. So the interpretation of a finite type, I'm going to make this named unit thing to describe just a unit, but keeping those names around. Sorry. And the interpretation of none is the empty set. The interpretation of 1 is this named unit type, and the interpretation of plus is the disjoint union. So these give us codes for finite types. Then we can talk about function types whose domains are finite. In fact, let me fit that on one screen. So I'm going to use this notation with an arrow to describe the inhabitant of the unit type. So that's so that the left-hand side of this doesn't carry any information. It's just for documentation that we can see the name of the unit type. And then just the rule for equality for those things. But then the interesting thing is this arrow type. So this is the type of functions with a finite domain. So A is a finite type, which is the domain of the function. And we define what a function from that type means by case analysis on that type. So there's only one function from none to a type, so that's just unit. For a singleton domain, we're going to talk about the named unit type. And for a sum type, then a function from a sum of 2 finite types is the product of the two types. So if a function accepts either an A or B, then that's the same as a function that handles all the A cases and a function that handles all of the B cases. So this means that all of the finite types essentially getting translated to big tuples of some sort. And we can write then lambda and application functions. So lambda turns an Agda type function from the interpretation of A to S into one of these finitary functions, and application turns it back the other direction. And both of these operate by just case analysis on the domain of the type. So to turn a function, which essentially means that you can turn a function from bool into a tuple of two things by case analysis on all of the possible arguments of the domain. And these lambda and apply functions like have the expected beta and data rules, although I've deleted something of beta accidentally there. So that means that if you take a function, you can convert it back and forth between the normal Agda function and this type of function. Then we can continue and define dependent functions. So dependent functions are tuples. This is when the domain is finite and each element of the tuple is allowed to be a different type. So this is essentially exactly the same as the previous definition. It's just this time we're using the previous definition to describe the type of the elements of the tuple. And that has exactly the same beta and data rules. And after which we get to write exactly the same definition of W types, but this time we're saying that the collection of places is a finite function. So each shape has only finitely many places, and the subtrees of a node of a W type are a finitary function from the places giving a subtree for each place. So now we can write the same binary tree type again, and here we say that the places are a leaf has no places and a branch has two places, one called left and one called right. We can write, as before, the leaf and branch constructors. And then we can write the same induction principle, but this time it all goes through straightforwardly because there's only one possible leaf and there's every possible branch is of the right form. Because this is not encoded with functions, they're expanded out to tuples. So this is a relatively well-known technique. It's sometimes known as normal functors, but the trouble is that it only works with finite numbers of places. And the new thing that I'd like to talk about here is how to extend this to types that might be infinite. So here's a simple example of a type with infinitely many subtrees, because it's a description of integer formulas. A formula is either a constant, one formula plus another one, or a big sigma, a sum from A to B, where the body takes the parameter of the index being summed over. So as a W type, this thing actually has infinitely many subtrees. There's one here, and there's n many here. And so if we were to encode this using normal W types with a big functional encoding, then we get the same problems with trying to talk about equality of functions. But the observation I'd like to make here is that if you use this directly in Agda, you don't actually get infinitely many variables to deal with. You get 3. There are 3 occurrences of the word formula in this type. One of them is under a function type, but there are only 3 different ones that have different equality rules. And the third one, even in Agda, you have to deal with the equality of functions yourself. So what we're going to do is describe this using partition sets. A partition set is a set that splits into finitely many components. It's given by a finite collection of parts, and each of those parts has a set of elements. And so this is like a type, and the thing that you can do with it is you can ask, given an element of it, which of the finite parts is it in? So these have, as before, we can define function arrows with the lambda and application rules for them. and then go through the same rigmarole of getting dependent types as well, with the pi types with their own Lambda and applications. And eventually, we get to be able to write this, which is an infinitary W type. Here, the set of places of a type is given by a partitioned set, and the subtrees are given by a partitioned set of trees. Then we can write the formula type, and the important thing is that the sigma constructor for formula types there are exactly 3 partitions, and the elements of each partition, the low only has 1, the high only has 1, and the body has not many of them. So this gets us the split that we see when we're writing these things manually in Agda between the finitary part, where you can only write the recursive type finitely many times, and still the ability to put infinitely many subtrees in as long as you're willing to use a function definition underneath. So with this one, we find that we can write the introduction forms as usual, but by separating the finitary from the infinite parts, we actually get to write the induction principle for these, and it works by straightforward case analysis in more or less the way you'd expect. Where the only really new part of this is splitting the finite from the infinite parts and treating them separately, rather than trying to combine them into a single definition and expecting both the good equality of tuples and having to deal with function equality. So, thanks very much.